Hi, I'm Fei from Sharcnet, and today I'll give you a seminar about the Intel's very new architecture. They call it Xeon Phi. And today I'm not able to show you the whole things about Xeon Phi. I just only give you a very basic introduction and show you what Xeon Phi is and how Xeon Phi works. If you have any other questions, then you can email me, and you can see my email here, and or you can submit a ticket on the Sharcnet web portal. And today we have several topics to talk, and the first one I want to tell you is that what Xeon Phi really is. And then we will have a deep look into its unique hardware architecture and software programming models. As Intel advertised, the previous CPU code can be run on Phi directly without changing anything. Well, can we really just recompile our previous code and make it running on Phi efficiently? Well, I doubt that, but I will answer you these questions. And next, I will show you some very basic, very simple example code in OpenMP and OpenCL and even the MPI. And I will also give you the optimizing guide, and also the performance result will be shown in this presentation. At last, and I will tell you how can we choose between Xeon Phi, CPU, and the GPUs. Okay, let's move to the first topic today. And the first topic is what Xeon Phi really is. And I remember the first time I heard about Xeon Phi is around 5 years ago. At that time, it's not called Xeon Phi. It is called the Larrabee project. And the MIC means many x86 cores integrated in a single chip. The Phi we have in Sharcnet is the P5 series. That means they have 60 cores per each. And Xeon Phi have 4 hardware threads per core. That means they can run 240 threads simultaneously on a single device. As you can see on the picture, and Xeon Phi looks like a graphic card, right? So it has active coding and passive coding options like a PCIe device. So it also used the memory like GPUs. It uses GDDR5 memories, and that means it will have a very wide memory bandwidth. And if you can see the picture below, and it shows you how the 60 cores connected with each other. And you can see that these 60 cores are connected through a ring bus, and it's a two-direction ring bus. And they also connected with the GDDR memory controller. And next, let's go deep look into the architecture in the single core and what's in the single core. Okay, if you ask me how to develop a high-performance application, I would also say that you should always keep hardware in mind. I consider there are 3 levels of parallelism. So the first level is the thread. As you can see in the picture, on the left top, and you can see there are the thread scheduler. Nowadays, we have multi-core CPUs, and even we have many core GPUs and Phis. So when you develop your parallel program, you have to make sure that your code can generate enough threads to fully use the hardware resource. So that means for Xeon Phi, you should create more than 60 threads. I mean, sometimes 120 or sometimes 240 threads in your code. And Intel says that the x86 logic is only 2% of the cores. That means this kind of x86 cores and the ALUs and the schedulers only use 2% of the hardware. But what's the rest of them? And next thing, and the very big thing is SMD, is a single instruction multiple data. Sometimes we call it vector unit or vector process unit. It's quite similar with GPUs. NVIDIA call it stream multiprocessors. AMD call it compute unit, or sometimes they call it SMD arrays. So the vector units use probably 80% of the area on the chip. So if your code don't use SMD at all, and it means you are wasting the hardware resource. You are wasting 80% of hardware resource. And the third thing, I consider it as a cache and a memory, because on-chip cache, the L2 cache or the L3 cache is on-chip cache. They have much more bandwidth and a much lower latency than the DDR memory. If you are trying to access the element in the DDR, and it will cost you a lot of time. But if it has already been prefetched in the on-chip cache, and you can access it very fast. If you can prefetch all the data you want into the on-chip memory, no matter it is L2 cache or L3 cache, or even they call them shared memory in GPU, it will greatly improve the memory performance if you prefetch all your data in on-chip memory. Okay, before I move to the next slide, I hope you can keep all these three things in mind. One is thread, the second one is SMD, and the third one is cache and memory. Okay, let's move on to the software part. And before that, I have to tell you how the Xeon Phi connected with the host. Like I said before, it's just like a GPU. You put the device onto the PCIe slot, and it is connected through the PCIe bus. So there are three main execution modes. The first one is called native mode, and the second one is offload mode, and the third one is called a symmetric mode. Okay, let's go through it one by one. The first mode is native mode. I think it is the easiest way to use Intel Xeon Phi. In this mode, you don't need to change your code. You just compile your code with the compiling flag -MMIC, and then the compiler will generate executable binary files which can only run on Phi. To have this program to run, you have to SSH to Phi's OS, and then you execute your program there. Okay, let me give you a very short introduction about the Xeon Phi OS. The Xeon Phi OS we call a sub OS. It's called a sub operating system. That means it can be treated like a host machine which runs a Linux kernel on that. So you can SSH to any of your Xeon Phi device, and you can list the file. You can use some tools like V, edit your files, and you can run your program on it. But be sure that your program is compiled with the -MMIC, so that they can be run on Xeon Phi. If not, your program can only be run on your host machine. Well, there is a big disadvantages if you're using native mode, is that the serial work will painfully slow. If you are running a serial job like reading and writing files, it will be painfully slow on Xeon Phi, because you know that each x68 cores is somehow weak and it's very old. It based on the Pentium CPU decades ago, so we can't expect to have a relatively higher performance is much lower than the modern CPU. Okay, so the next mode is the offload mode. The offload mode means that you treat the coprocessor just like GPUs, and the CPU runs the host code in serial or in parallel. It doesn't matter. But when you need the job to be run on Phi, you offload the job on Phi. The only thing you should add to your program is a directive. It's a directive called pragma offload, and you have to specify the target. I mean the target MIC0, and you have to specify the array that you want to put onto the Xeon Phi, and you have to specify the in. That means this memory should go into Xeon Phi, and you can also use out. That means this memory only comes from Xeon Phi to the host machine, and you can combine them like in out. That means you have to read and write this array on Xeon Phi, and after that you just put your code. I mean massively parallel code running on the MIC, running on the Xeon Phi. It's quite simple and easy for you to add some directives into your code and make it run on Xeon Phi. And the last mode is called a symmetric mode. While in symmetric mode, we often use MPI to communicate between the host and the Phis. And that means you have to prepare two kinds of different executable binary files. One is for host, and then another one is for Phi. So you compile two kinds of binary files, one with the -MMSC flag, one without the -MMSC flag. After that, you can use MPI call, and you can allocate the jobs, allocate the MPI ranks onto different devices. For example, you can allocate 12 ranks on the host and 240 ranks on the Phi. Well, there will be a problem. There will be a load balance problem, because if dealing with only one rank, and the host will be much faster than Phi, because the host have much stronger core. So you may probably need more ranks running on a host. Maybe you have 100 ranks running on your host and 240 ranks running on the Phi. Well, it really depends on your code. I mean, it really depends on what kind of code you have. Okay, next, and I will show you some example codes, a very simple example codes. And it's really hard to choose a perfect example to teach people how to do parallel programming. I remember when I learned OpenCL programming, I found that both Apple and AMD use convolution as an example to show people how to optimize these performance things like that. So I choose a convolution as an example for the OpenMP and the OpenCL, and I will use Intel's example for MPI. If you search MPI Xeon Phi, you will find it on the Intel website. Well, Intel only used this code to show the basic usage of MPI on Xeon Phi, but I modified the code to improve the performance, and I will show you later how to modify the code to improve the performance. Well, I'm not quite sure how many of you are familiar with the two-dimensional convolution operations. What is quite easy? You just, for example, if you have an image here on the right and in blue, and you have a kernel in red, you just calculate every element one by one and sum them all. It's just like a dot product, here. And you can see the program code on the left is quite simple, and I will show you how I organize the thread and SMD. In this example, I use one thread for one row. That means one thread calculates one row of the image. So we put the Pragma OpenMP parallel 4 on the outer loop. The outer loop is iterate the rows. So, and the inner loop are using for the different columns in the rows. So I put the Pragma SMD to tell the compiler that you can calculate them. They don't have anything dependent, so you can calculate them in SMD units one by one, and you can put them put a bunch of them, maybe 16, maybe more, into the vector unit and calculate at the same time. And there was a tricky part here, is called a Pragma on row. If we know the size of the kernel, we can write things like this, like a constant value here, 3 and 4, because we have 7 by 7 kernels. We don't have 3 by 3. We have 7 by 7 kernels in this example. So if we do know the size of our kernel, and we can tell the compiler to unroll the for loop, and it will help the SMD unit to run more efficiently. And in this loop, and it's just a dot product operation, just sum them all, and at last they just output the image, and it's quite easy program here. And I will show you the result. Okay, for this two-dimensional convolution, and I'm using a very huge image to test it, and it has 120 megapixel in grayscale. And we have 2 Xeon CPU on Goblin node 49, and each of them are 6 cores with 15 megabytes L3 cache. So that means in total we have 12 threads for CPUs. And I tested different thread on Xeon Phi. You see the 60, 120, and 240 thread. And the time column shows the program without unroll the for loop. If we don't unroll the for loop, and we can see the CPU runs half second and the Phi runs nearly half a second like that. But if we unroll the loop, and the CPU performance is greatly improved, and it reach a result of less than 100 milliseconds. But for Xeon Phi, it improves, but not that much. So the Xeon Phi is still lower, it's still slower than the CPU. And why? Do we forget something? Like I tell you before, you keep 3 things in mind. One is threading. Yeah, we consider about threading. We have 120 thread already. And we consider about SMD, right? Right. We use the Pragma SMD directive to tell the compiler to auto-vectorize the code. We use SMD, but we forgot the cache. The CPU has a relatively larger on-chip cache. Like I said before, each CPU has 15 megabytes L3 cache shared by the 6 cores, and in total we have 30 megabytes cache here. That means we can cache so many rows of the image into cache and read them very efficiently. But for Phi, each core has only 512 kilobytes. So we cannot prefetch too many rows of image into the Phi's cache because we don't have enough room for them. So if we want to exit, our convolution is two-dimensional. So we have to, if one thread is working with the row 1, and we may need the data in row 7. So we don't have enough room to hold all these 7 rows into Phi's cache. So if we want to access the elements in the row 4, row 5, and we have to find them in the DDR memory, it's very slow. But for CPU, and we can prefetch maybe 100 or 1,000 rows in the cache memory. So it doesn't. So if you want to access the rows next to them, maybe row 5 or row 7, and it will be in the on-chip cache. And I will use the OpenCL to show you how to manage the cache memory. Well, OpenCL is something just like CUDA. I'm not quite sure if you know CUDA a lot. If you know CUDA, and OpenCL is just like that. There are only some different names and different API calls. Well, the first thing I want to show you is how OpenCL maps to the Xeon Phi. It's the same as CPUs. I mean, one work group is called block in CUDA. That means one work group maps to one hardware thread. And we have 4 threads each core, right? So we can have 4 work group running on each course. And each work items in the work group runs on the SMD unit. I mean, runs on a vector unit. And the work item is just like a thread in CUDA. So we have 2 different kind of kernel here. The first one is just like the OpenMP example previously. It has 1 work group per row. That means 1 thread per row. And we can also have a 2-dimensional kernel. That means 1 work atom per pixel. It's not like a 1 thread per pixel. It's just 1 work atom per pixel. That means 1 unit in the vector unit, 1 element in the vector unit per pixel. That means if we have a vector unit with the length of 16, that we can run 16 work atoms on this vector unit simultaneously. So the result is obvious. So the first result is a 1-dimensional kernel, like our OpenMP example, and it costs 200 milliseconds. But if we are using the 2-dimensional kernels, and which have the 2-dimensional kernels has better memory cache management. Why? And because if the kernel is 2-dimensional, and that means we need in 1 thread, I mean in 1 work group, we need not only 1 rows but multiple rows. We need 7 rows or maybe more. So the compiler or the OpenCL runtime will prefetch all these 7 rows in the cache. Not only 1 row, but also the 7 rows or maybe more. So if we were trying to access the elements in different rows, they have already in the cache memory. And we can do it manually, like when we program CUDA code, and we can put all these 7 rows into the local memory. And the local memory is called the shared memory in CUDA. Then we have to synchronize them because different threads are running different times, and you need to synchronize the thread in the block. But if you use the GPU code on Phi, and it won't give you better performance because the first Xeon Phi don't have local memory. If you are using local memory in the OpenCL, all local memory will map to the DDR. You cannot control the L2 cache memory. And you don't need to synchronize them because All work atoms in the work group runs on the vector unit one by one. They are in order execution, not out of order execution, so you don't need to synchronize them. So if you are using local memory and the synchronization, and it will slow down your program. That's the reason why you cannot use your previous OpenCL code optimized for GPU and let it put them directly on Xeon Phi. It will show you a very good result. You can see here, it's 80 seconds is a quite good result, but it won't reach the hardware performance limit. It won't give you a peak performance on Xeon Phi. So the next example I want to show you is the MPI example. So in MPI, one MPI ranks maps to one hardware thread. That means you can have 240 MPI ranks running on the Phi coprocessors. And you can use MPI to communicate for the communication between the Xeon Phi and the Xeon CPUs. And I have to point out that each thread in this code, in our code example, it's a Monte Carlo estimation of pi. I'm sure you know Monte Carlo estimation of pi is that you generate a bunch of random number between 0 and 1, and you calculate the number which have a distance. The readings in the circle. Each point located in the circle. In the square, you generate a bunch of random numbers, and you calculate how many numbers are in the circle, and you can calculate the pi. And I will show you the result first. And as you can see here, the Xeon CPU is better than the Xeon Phi. And we must forget something. And we will check the three big things again. The first is thread. Yeah, we have multiple thread here. We have 120 thread. It's enough. And the second thing is SMD. Well, in our code, we don't use SMD, and I will show you later. And the third thing is the cache. Why is it random number generation problem? You didn't use a lot of memory. You just create the random number in the register and calculate them, and you only need to put them back to the memory for the result. You don't need to access the memory very frequently. Okay, let's move on to the page for the code. Well, the code on the left is a pure MPI code, just Intel gave us. And this for loop is only in one rank. Oh, I just had the details about the rank and about the communication. I just want to show you what happens in one rank, or you call it one process. So for each process, for each rank, it uses a for loop to generate a bunch of random number, and you calculate the distance between the number to the circle point to the center, and if it's less or equal to 1, and you just iterate them and calculate them and treat them as a point instead, and you calculate how many points are inside the circle, and they will give you a result. And you see this code, they don't use vector unit at all. So we have to think about a solution to use the SMD unit. As you can see the code on the right here, I put a pragma SMD and some private variables here. But you can't just put the pragma SMD in before the for loop on the left, because we have some variables that add themselves. So we cannot let all the SMD unit to read the same register, to read and write the same register. We have the RISC problem. So to avoid the RISC problem, we just put the result in the temporary array. The temporary array, the TT point here. So we put the result into a temporary array, and after that we use the reduction to calculate how many points in the array are as a flag 1. They have a temporary value 1. If it equals 1, that means it is in the circle. If it is equal to 0, that means it isn't in the circle. So we only have to sum them up. Then we can know how many points are in the circle. So you just put the SMD here, and let's see what the result is. So here is the SMD speed up for the code, and you can see for Xeon CPU we don't have any speed up, but for Xeon Phi we have a 50% improvement on this code. Well, let me explain you why the SMD doesn't help the Xeon CPU. Let's go back to the code here. So you can see we use the temporary array to store the temporary value here. Where the temporary array is in DDR. Accessing DDR is painfully slow compared with accessing the register. So the CPU and the Phi will have to write the data to the DDR memory and read them again for the reduction operations. The CPU has a relatively lower DDR memory bandwidth. It's around only 50 gigabytes per second, but Xeon Phi has 160 gigabytes per second. So that means the DDR memory controller is much faster on Xeon Phi than CPUs. So if we're using SMD, and it can speed up your code maybe around 8 times or 10 times, but considering the memory latency, and the speed up won't reach that high, and we get only 50% speed up here. And if you need more speed up, and you can store your code, you can store your data in the register or maybe in cache memory, but it's quite complicated. You have to use the SSD instructions, something like AVX instructions like that. So you can reach maybe you can reach 5 times faster code. But I'm here to show you the simplest way to improve the performance for your code is that you use memory, and you write them into memory and read them from memory. And if you can fully use the SMD unit, and it will give you 50% speed up. It's quite good, right? So you can see here, if we can use MPI to communicate between Phis. So we have 2 Phis here, and it almost double the speed, and it costs only 2 seconds compared with the 4 seconds here. Okay, the next big thing is, how can we choose? Which one should we choose? Xeon Phi, CPU, or GPU? First, I'm going to compare CPU with Xeon Phi. And they are in the same architecture, in same x86 architecture. So that means your code can run on both of them. If you don't want to change your code, you can run them on native mode. If you want just adding some offload directives, and you can run it on offload mode. So the first questions you have to ask is, are you using the library like MKL for large size linear algebra problem? If so, I will highly recommend you to use Xeon Phi. You know that the GPU has much higher linear algebra performance than CPU. Xeon Phi is in the same situation because they have many cores and they have many ALUs in it, so it's very suitable for the large size linear algebra problem. So if you are using MKL, use Phi. And the next things you have to consider is if your code use more than 100 threads. Well, in our MPI example, we use more than 100 threads, but the Xeon Phi is still slower than the CPU. So if your code only use 100 threads, I doubt if it can run efficiently, it can run faster on Xeon Phi. You can try, but I don't think it will be much faster than the CPUs. But if your code is very suitable for the large vector operations, and that means your code is vectorized, you can vectorize your code, or you can let the compiler vectorize your code. If you have vectorized the code and you also have 100 more threads, and I recommend you to try Xeon Phi. Well, if your program use memory a lot and it really needs a very wide memory bandwidth, and you can try Xeon Phi. Well, it's a choice between Xeon Phi and the CPU. Let's move on to the next. Okay, how can we choose GPU and Xeon Phi? Well, if you don't know GPU programming and you have your previous CPU code, well, your code may not be optimized, but if you have multi-thread CPU code, and I recommend you just modify your code like I do, just add some SMD directives onto your code and try it. If you have previous CPU code and you don't know how to program GPU, and I recommend you to use Xeon Phi. And if you have already learned how to program in CUDA or OpenCL, and I recommend you to use GPU, not the Xeon Phi. But you can try Xeon Phi. You can port your CUDA code to OpenCL, and the OpenCL can run on Xeon Phi. You can see, and I will give you a result compared between the Xeon Phi and the K20 GPUs. I have the same kernel. It's a two-dimensional convolutional kernel, and the first one is we don't use any local memory. I mean, we don't use shared memory. It just use the cache, and you can see that the Xeon Phi is faster than GPU. Why? Because Xeon Phi has a lot of memory, on-chip memory, and it has 30 megabytes in total, but the K20 has only 2 megabytes. So as you can see, the Xeon Phi will win in this situation because we don't manage the on-chip memory by ourselves. We just use the prefetcher to do it. Well, if you learn how to program GPU, you have to know how to manage the on-chip memory. I mean the local memory, or you call shared memory, whatever. And if you are willing to manage the memory all by yourself, and I will highly recommend you to use the GPU. And I write a kernel. I write a kernel with the local memory in it, and in K20 it will achieve a much higher performance than the Xeon Phi. As you can see here, it cost K20 only 38 seconds to finish the job, and the Xeon Phi needed 70. So it's much faster on K20 GPU. So if you know how to program GPU, if you want to optimize your code, then use the GPU. if you don't know how to program GPU, if you don't want to spend a lot of time on optimization, the on-chip memory, you can try Xeon Phi. That's my suggestion for the GPU and Xeon Phi. And so the conclusion is now you can see we have multiple questions and we have already answered them. So what is Xeon Phi? And it's many x86 cores on it with the large and the advanced vector units. And the second thing is the hardware matters. Yeah, the hardware matters. Like I told you before, you have to consider about the threading, consider about the vector unit, consider about the cache miss and cache hit here. And I have already introduced some kind of running models, how to run native models, how to run offload model, and then symmetric models, and I'll also give you some OpenMP and OpenCL and MPI code here, and I'll also give you some suggestion about how to choose the Xeon Phi CPU and GPUs. So let me show you some references here. We have some documents on Sharcnet website. And if you go into the wiki page, and you can find some kind of Xeon Phi coprocessor problem related with the Goblin cluster. In here, you can find how to log into the Goblin cluster, how to log into the Xeon Phi node. And I also write a programming guide for Xeon Phi, and you can find it on Programming Xeon Phi wiki. And if you are familiar with the CUDA and you want to try your previous CUDA code on Xeon Phi, and you have to port your CUDA code to OpenCL, and the OpenCL can be run on Xeon Phi. Okay, so that's for the slides, and next I will show you how to log into the Xeon Phi node and how to compile and run programs. Okay, so first we log into the Goblin node. After we log into the Goblin node, we can SSH to the Xeon Phi node. It's called a Goblin 49. Then we log into the Goblin 49, and you should know that there is no modular here, so the modular doesn't work here. There is no modular here, so we have to export the path by ourselves. It's quite simple. You can use source, and you find where the Intel compiler is. The Intel compiler. You have to use at least Intel compiler 14. So you need at least the 14. And use the Intel compiler for C, and we just export the path here. Use compiler various sh Intel 64. Okay, after that, the computer can find the compiler. Let's see which ICC. So you can see they know where ICC is. And I'm going to my example folder. Let's see. It's 5 examples. Show you the OpenMP as an example. It's quite easy. So I have 2 C files, one for loading the image, one for calculating. First, we compile the image part, the image operations. And be sure you add the -MMIC as one of your compiler flags. So we have VM functions. That means -O-C, so we have VM functions there, .c. So this command will compile compile the image operations to an object, and let's compile the computing part. Dash OpenMP, because it's OpenMP directives in it. And the object file is, so we call them OMP 2D conf MSC object, and the source file is OMP 2D conf. (120 thread examples here). Okay, after that we link them together. OpenMP-O. We can have a name OMP 2D -MSCX. That means MSC executable files, and we have MSC object, and we have our OMP 2D conf object, MSC object. Okay, just ignore the warning. And now we have an executable file named OMP 2D .MSCX. Can we run it here? No, we can't run it on host. We have to log into the Xeon Phi sub OS. So we SSH to one of our Xeon Phi card, maybe make one. And here in make one, you see that we can still use list to list the file. We just mount the file on Xeon Phi, so you can access your file home folder. You can access your home folder, and there was no work folder, but we have the global work folder. So if you know which global work you are in, for example, I'm in global A, so I just open global A work, my name here. So I can access my file in global work. Okay, let's go back to the home folder, and we find where our executable file is. It's Phi example. It's file example, and it's called OpenMP. Okay, OMP 2D conf. 2D conf. Let's check the name. Okay, we have OMP 2D .MSCX. Okay, so we can execute it here. It's OMP 2D .MSCX. Yeah, you see, you can run here. So this is very basic usage for the Xeon Phi, and you can, if you're running the offload mode, and you just run it on host, only you are using the native mode, you should log into the Xeon Phi, subsystem here. So if you're running MPI code, or if you're running the MKL offload code, or any offload code, you just run it on Goblin 49. And I'm afraid I don't have enough time to show you how to run the offload code, but it is quite easy. It's just like, if you want to know more about the Intel Xeon Phi, and you can go to our website, Wiki website, or you can, if you have any questions about Xeon Phi, you just email me, or you submit a ticket on our web portal. So that's all for today.